So welcome to the webinar series of the INAE Chennai chapter. Welcome all of you. So a special welcome to Professor Krishnan Balasubramaniam, who is the speaker today in the webinar. So he will be talking on a topic, asset and process integrity monitoring, a lab to market journey. So before he starts the lecture, I'll just give a brief introduction of Professor Krishnan Balasubramaniam. Professor Krishnan Balasubramaniam is the institute professor at IIT Madras and serves as the head of the Center for Non-Destructive Evaluation, which he founded in 2001. He also directs the Gopalakrishnan Deshpande Center for Innovation and Entrepreneurship, which focus on lab-to-market space in India that has influenced 1,300 entrepreneurs and 330 faculty leads. He has over 530 technical publications, including 290 in refereed journals, 46 patents filed, and he has guided 29 PhD scholars and 55 MS scholars. He also served as the Dean of the Industrial Consultancy and Sponsored Research Program at IIT Madras for 6 years, and he had initiated several new initiatives in that position that fosters an improved research and innovation ecosystem at IIT Madras and further improving the industrial relations and intellectual property generation. He was also instrumental in creations of several new centers of excellence in IIT Madras, including the Center for Railway Research, Center for Advanced Automotive Research, Center for Advanced Manufacturing Technologies, and Robert Bosch Center for Artificial Intelligence and Decision Sciences. He has been bestowed with the prestigious Abdul Kalam National Technology Innovation Award, DRDO Academic Excellence Award, Roy Sharp Prize, UK, as well as the Lifetime Achievement Award by the Indian Institute of Technology, Madras. He is a fellow of the INAE and NACI and a distinguished alumni awardee by his alma mater, NIT Tiruchirappalli. He was recently awarded the INAE Chair Professorship in 2023 for a period of 3 years. He has been the founding team member of several startups, including Dhwani Research, Plains Technologies, Detect Technologies, Maximum Labs, Zyma Analytics, and Solinas Integrity. So with this rich bio, I request Professor Krishnan Balasubramaniam to give his lecture on a journey from lab to market. Professor Krishnan Balasubramaniam, you can start. You can speak for about 45 to 50 minutes, which will be followed by a question and answer session. I think Professor Ashish Sen will be monitoring the question and answer session. So, Professor Krishnan Balasubramaniam.
Thank you, Professor Narayanan. It's an honor, pleasure being among esteemed colleagues of INAE and many other participants who will be joining the program today. Thank you, Ashish, also for inviting me here. What I'm trying to today talk about will be in the field of non-destructive testing, which is my favorite field. And let me give me 1 minute, please. Okay, where I'll be talking about a particular technology that has been my passion for the last 30 years or so, maybe more than that. I did my PhD, and PhD was in the area of ultrasonic waves that are guided by the geometry of an object. In fact, I remember way back in 1986 or so, when I was a grad student, my professor came and put a paper on front of me and said, Krishnan, this is something that I want you to look into and figure it out. And I gladly accepted it, only to realize that the whole paper was in German. And so I had to find somebody to translate it for me, at least partly. And then that kind of started my journey on guided waves. My PhD thesis was on using guided waves for
Professor Krishnan, you can come on video.
So what happens is that, so that's kind of started where I spent 3 years trying to figure out how porosity in composites and the anisotropy in composite materials affected the propagation of ultrasonic guided waves and how you can actually use that information to measure certain properties of composite materials, particularly of application in the aerospace industry. Now, just a brief background. I'm going to talk a few minutes about our center and non-destructive testing, but I think it needs no further emphasis that non-destructive testing methods are extremely valuable to the industry because materials degrade, components gets damaged, and the assessment of these components either in the early stage of manufacturing or in the stage of raw material inspection before manufacturing, and in the field of in-service inspection where the component is in service becomes very valuable. And the technologies that are used in non-destructive testing are very similar to what's used in medical. So we use X-rays, we use visual, we use sound, acoustics, ultrasound, infrared, and very similarly we use an NDE. And the big difference between what is the problem that they have in medical field to what you have in non-destructive testing is the fact that the problem statements are very different. You have new material system that's coming up on a regular basis. Every couple of years, you're looking at new problems, new materials, new issues, new designs. Another major issue, particularly in service, is the large volume of material that needs to be inspected. So if we talk of a bridge, a single bridge is huge, and the number of components within that bridge is phenomenally large. Same thing happens if you talk in terms of, say, a rail of a train, the rails that are used to travel, used by the railways. You have thousands and thousands and thousands of kilometers. Same as with pipelines. Pipelines, either if you're talking in terms of what's called the inside the battery pipelines or cross-country pipelines, the volume is very high, and many times these pipelines are buried, for instance, or your component may be inside a nuclear power plant, or it could be inside a fairly aggressive temperature situation. So the question that comes up is, given those problem statements, how do we actually try to assure the performance, the quality, and more importantly, you have to worry about cost in all of this because every penny or dollar or rupee that you spend on this translates into overall cost of operations. So with that in mind, how do we actually go forward? So there are many ways by which we do that. If it's an inspection system during manufacturing, then you start to use robotics to reduce the cost and improve the speed. You try to use non-contact. You try to use large volume inspection tools. Use robotics. You use, you can also go towards what's called health monitoring and remote diagnostics, which is becoming more and more popular. Now, we are absolutely doing the same things here. For instance, I'm just showing you 3 simple videos, whether it is underwater structure or whether it is on the surface or whether it is a little bit above the surface. You can use robotics to speed up inspection. You can also make inspections safer instead of humans going at these heights or underwater or anywhere. The speed, the reliability, as well as the cost, all implications allow you to actually look at these kinds of robotics as one of the tools by which you can actually make it better. So as a group, we are interested in looking at deep research and with industrial applications as well as societal well-being. When I say industrial application, it could be a wide range of industries. And when we talk in terms of societal well-being, we are talking in terms of the pipes that bring water to you, the sewage that takes away stuff from your home, and and so forth, as well as the road in which you travel, or the train or the plane in which you are actually moving on. Our team is small. It's about 8 faculty members of IIT Madras, and very wide spectrum of specialization. across several departments. If I look at what we do, we look at three major components. One is non-destructive testing and imaging, either, as I said, during service, manufacturing or post-manufacturing doing in service. The idea here is, can I develop technologies that makes it faster, cheaper, and also do things that is considered not possible. Now, it's always possible to move these sensing technologies into a health monitoring mode where the sensors are permanently installed on the sensor or in the sensor, and thereby you are completely changing the way the sensor, the structure or the infrastructure is managed, wherein real-time information allows you to extend the life beyond the normal life and reduce the periodicity of shutdowns and inspection. Finally, these sensors can also be used in terms of measurement. And I'll show you that today that we actually can go up to 1500 degrees Celsius in measurements in very hostile environments. So coming to ultrasound. Ultrasound, as all of you know, is acoustic waves. In materials, they may be called as stress waves. And typically, they are divided in two terminologies. The first terminology is called as bulk waves. Bulk waves are the classic longitudinal wave mode and the classic shear mode or the transverse mode. And they are both elastic waves, and these elasticity are related to density and the Lemaire's constants that you normally will subscribe to. Now, unlike, say, a vibration paradigm, where the modes are described by the frequency in which it occurs, we are very particular that the wave modes are defined by the relationship between the propagating vector and the vibrational vector. So the angle between the two often defines a difference between a longitudinal wave and a transverse mode. But if you go to slightly more complicated wave modes, like the Rayleigh wave mode as shown in the bottom, then what you see is that it actually has an elliptical wave mode pattern in terms of vibration. Rayleigh wave mode is one of the earliest guided ultrasonic wave mode that you would normally see. So you tend for these wave modes to have certain mode structure as they propagate along the geometry of the structure. Now, coming from an industry point of view, the guided waves was conceived as a very useful tool because unlike the traditional ultrasonic waves, which are bulk in nature and hence can be looking at only certain small regions of interest, the ultrasonic guided waves have the advantage that they actually insonify a cross section, and thereby you can inspect larger areas. You can inspect areas much further away from where you are generating the sound waves, and that was a key attraction that was sought after many years ago. Now, there are certain advantages. There are a couple of different ways by which you can actually generate these waves. For instance, you can generate these waves by using a plastic angle wedge. So when you insonify a wave of a bulk type at a particular angle on a geometric of a structure, which is able to sustain the guided waves, then due to the multiple interactions of this wave mode within the structure, at the right frequency, at the right thickness of the component for the particular material property, a guided wave can be generated. Now, depending on the angle, more than one guided waves can be generated, and it also depends on the divergence of this beam, and so you're insonifying it at multiple angles, and you can get multiple wave modes that can be simultaneously generated. An alternate to this kind of generation is another generation called as Coombe transducer, where you have periodic piezoelectric crystals that are exciting the space just below that. I'm sorry. And then you get a periodic excitation that eventually interferes with each other and forms a propagating wave called a guided ultrasonic wave. The key difference between the two modes is that the one that's called as the Coombe excitation, actually the wavelength is fixed and the spacing defines the wavelength because the spacing is equal to lambda by 2, and hence you can actually have a fixed wavelength that is moving along. On the contrary to that, when you do by the insonification at an angle, then what happens is the angle defines what is the wave mode that you're generating, and the frequency at which you generate will be separately looked at. Now, guided ultrasonic wave modes are not uncommon to humans. We've done that as a child, and it can be almost anything that has some sort of a geometrical confinement will be able to generate a guided wave in these kinds of confined spaces. So it can be in the form of plates and shells, rods, cylinders, layered media, you name it, you can actually generate them. And of course, many of us experienced it, I think, in the year 2005, wherein on 26th December, we got the tsunami wave. That is one of the most interesting and classical structure of a guided ultrasonic wave, where you had one mode that came on the water surface and another mode that came between this interface between the water and the soil itself. Classically, these wave modes are nomenclatured depending on the geometry in which the wave mode is generated or confined. So in a plate-like structure, you can have three types of modes. One is called the anti-symmetric mode here. Another is the symmetric mode here. And finally, there's something called shear horizontal mode here. The difference between the three is that the anti-symmetric mode, if you look at the top point and the bottom point of the plate, they move in synchronous. So they are not symmetric if you draw a line which is along the axis. The symmetric, on the other hand, if the top point moves up, the bottom point is also moving down. And hence, if I draw a line in the middle, then the mode shapes are symmetric. The horizontal shear mode is more where the displacement is along the line that is perpendicular to the axis of the thing, which means it's going into the wall or into the board. Now, when you go from a plate and you solve the equation for a wave mode that is going to be either in a cylinder or in a rod-like structure, obviously you have a cylindrical coordinate system that needs to come into picture. But there are a lot of similarities. For instance, the S0 mode is often called as the longitudinal mode in a rod, wherein the vibration is along the axis while the wave is also propagating along the axis. A flexural mode, on the other hand, is unsymmetric mode, where the perpendicular, the vibration is more radial in nature, and again, in all the cases, the propagation is axial. Torsional, on the other hand, is like the shear horizontal, where the vibration of every point on the cross section is circumferential, or in some ways, it's the vector points is pointing always in a tangential direction to the surface. So these are different wave modes that can be generated, and the nomenclatures are as A, S, and SH in the top in a plate. When you go to the cylinder, this is called flexural F, longitudinal L, and torsional T. Now, in addition to that, you have a number there, and these are what I call the wave mode numbers, which means that the 0th wave mode is the fundamental wave mode. Your configuration of displacement or mode structure is more basic. As the number increases, then the wave structure becomes more complex. Unlike the plate, when you go to a cylinder, you need two numbers to define it. The first number basically defines whether the wave mode is axis symmetric or not. So for instance, the flexural mode is never axis symmetric. So the number M will take a value of 1. The longitudinal and the torsional are likely to be symmetric or axis symmetric, and hence the value M is usually taken a value of 0. And again, N, like before, is a number that will define the mode order. So the higher the number, the more complex is the mode shape within the structure. Now, one of the ways by which you can map this is a plot called a dispersion curve. There are a couple of different ways by which the dispersion curve is plotted. In our area of non-destructive testing, we tend to plot it between a velocity, which can be phase velocity or group velocity, as a function of frequency thickness product. The reason why frequency thickness product becomes important is because in a plate-like structure, this is confounded effect. So they come together. So frequency and thickness cannot be separated out. When you go to cylinders, again, you have three parameters that are coupled: the frequency, the thickness of the cylinder, as well as the diameter of the cylinder. All the three are coupled together. Now, here I'm only showing the the symmetric and the anti-symmetric modes. So the fundamental mode shape is like this in the blue color for the anti-symmetric, and S0 is for the symmetric modes. And then the higher order modes are shown right here. Now, the only difference is the fact that the anti-symmetric mode or the fundamental mode is the only one that has sort of the curvature that is different from all other modes. And also to say that this is the only mode that does not have what's called a cutoff. All other modes will have a frequency cutoff where they actually go up and be asymptotic to the vertical axis at some point or the other. One other point I want to make is that as this is curved and the curvature is increases, then you have a velocity is changing as a function of frequency or thickness, and this effect is dispersion effect. And the dispersion effect is more when the curvature is more. So a region like this is more dispersive compared to a region that's flat where the velocity doesn't change significantly with frequency or thickness. So the question is, what is the significance of that? Significance of that is for finding defects, you're better off using non-dispersive or modes in the regime that is flat. When you're trying to measure thickness of a component, then you may want to go to these sharply changing curves, because thickness is then becomes a function here, so that by figuring out the velocity change, you can start to, or at a fixed frequency, you can start to measure thickness. So dispersive and non-dispersive regimes are very important. You can see the S0 mode is non-dispersive in the lower frequencies, becomes dispersive at medial frequencies, and towards the later part becomes somewhat non-dispersive. So depending upon the mode selection is critical. It's also very important to actually find which regime of frequency behaves in which way. So the effect of dispersion is very clearly shown here. Here is a signal of an ultrasonic signal of a guided wave. If you selectively do it in a non-dispersive medium or a non-dispersive zone, the shape of the signal remains the same. However, if you are in a dispersive zone, then the frequency starts to affect the velocity, and very similar to a prism splitting up the light to different wavelengths, you have something very similar where the lower frequencies in this case are coming later, the higher frequencies are coming earlier, which means that the higher frequencies velocity is higher, the lower frequency velocity is slower. So very similar to splitting the the light, white light, you can do the same thing with a broadband input and be able to see the dispersion effects quite nicely. Very good for measurement of material thickness, not so great if you want to measure defects or get defects. So that's exactly what is seen here. So you will pick the right zone, generate the wave mode, either using the Coombe type or the inclination angle type, and then you can be on your way. Why are we interested? Many applications are there. Large volume inspection makes the job much simpler. But even more important is the fact that these wave modes can travel long distances. So you can actually generate the wave in one part, and then launch the wave and then be able to inspect or to make measurements somewhere far away. So sometimes you can do that in hidden regions also, which you'll see a few examples of. Also, the multi-mode nature allows you, while it may be a little bit more difficult to interpret, the advantage is that there's more information that's available. So different modes can give you different information, content, and that can improve the ability to characterize materials. So most likely guided waves are classified based on the geometry of the structure in which it's traveling, or the type of relationship between the vector of propagation vector versus the vibration vector. Also, the symmetry might actually come into picture, and depending upon who was the first one to discover these modes, you can actually talk in terms of Rayleigh, Scholte, Lau, Shizawa, and so forth. Now, for industrial applications, particularly non-destructive applications, this was not much talked about. As I said, I got to know about or hear about guided waves in 1986 timeframe, and that's kind of when people started talking about it. But by 2000, a lot of applications were solved and things were available. And since then, industry has accepted it. There are guidelines, there are codes, there are standards that are already in place. And finally, today, it's fairly well used by the industry across the platform. So I will start by sharing some initial work that we had done. So as I said, in the mid 80s to late 80s, I'd done a lot of work on porosity measurements for aerospace industry. And between 1990 and 2000, I spent a lot of time in trying to create certain complicated composite layups that will allow for the wave to actually take preferential directions. A lot of it has to do with the stealth and acoustic isolation of composite structures. In the early 2000s, we started working with the local DRDO labs and ADA and NAL, where we started looking at structural health monitoring of composites using guided ultrasonic waves. A couple of examples I'll show in a minute or two. And one of our claim to fame was that we were able to instrument a flap of light combat aircraft with these guided wave sensors, and we were able to show the genesis as well as the growth of defects like delaminations in them. So here are some examples from that work where we created a central transmitter piezoelectric transducer with a bunch of receivers around it. What we were able to do was to actually quantitatively measure the elastic moduli, and in this case, an orthotropic assumption. So 9 elastic constants could be measured by generating the S0 and the A0 mode. And we were able to measure these, and we were able to match this within a couple of percent of the actual measured value using destructive testing. So this means that I can actually take this and measure the elastic properties of actually as manufactured structures. Now, once you have that, then it is possible also to use it in a structural health monitoring mode where you start to pick up defects. So if you look at this as a composite plate, and what you're able to pick are defects that have been generated by impact loading. And so this particular work was something that we are very happy about. And we were able to show that in actual structures, because unlike a plate, the actual structures are far more complicated. So we were able to create structural health monitoring along with all the electronics and everything for monitoring these light combat aircraft structures. Around that time, we started getting interested in air-coupled ultrasonics. The difference between air-coupled ultrasonics and conventional ultrasonic is the fact that the conventional ultrasonics requires a medium between the piezoelectric crystal and the material itself. And often that's not liked by certain applications, particularly when you go to aerospace applications. So we started working on air-coupled guided waves. And as we go along, we actually have worked very closely with a lot of industries. So this work started in around 2007-8, and at that time, one of the biggest problem was that even with using air couple, you needed access to both sides for inspection. So the question is, how do we do that from single side? And that's where guided waves come into picture. So I had two PhD students who work on this, we were able to discover something called a turning modes that later on became very popular because many other companies like Bell helicopters, Sirkos helicopters, all of them started using this for a couple of interesting applications. Then we were able to actually transfer some of this technology to the industry. And then today, many installations are available in DRDO and ISRO and other places for composite inspection using these technologies. In fact, as recently as last week, there was a guided wave technology that was transferred to DRDO. Now, interesting thing here is that we discovered something called turning modes. So wherein if a wave mode is going in a composite in one direction, if there is a sharp bend, then we found that the wave actually, a part of it goes right straight through, but a part of it actually comes around. So for certain applications like a J in a composite, it's called a J configuration, wherein instead of using a joint, it becomes co-cured. So when you have this sharp corner, stress intensity factors actually will play a role, and then you could have delaminations that is initiated at that point. So the question was, can we find it? And if so, can we size it? So several samples were made. And what we were able to show was if you are able to try to pick up the mode that is going in from right to left, but then due to this particular sharp corner makes a turnaround, the time it takes to go around is much more. So if you look at a blue signal here, that is a normal joint. The green, you have a delamination, and the red is a larger delamination. Two things are happening. The time is changing, so are the amplitudes. And the amplitude is changing more because it's getting attenuated because of the longer travel. So we were actually able to characterize these kinds of defects quite accurately. Another example, this is a company based out of US that is making these nacelles. Nacelles are the composite material that is the shell of an engine. So these are the composites right around, and to make it light and stiff, they have these stringers. This is not uncommon. So this is like a base composite, and then there's a stringer that's bonded or co-cured. And the problem they have was they didn't know how to inspect this particular area once it is in place because you have it facing the engine. So what we have done, and another problem that people are talking a lot about is the noodle region. This is the triangle, often called the Bermuda Triangle. And that's another area where defects do come up during manufacturing. So what we came up was an air coupled ultrasonics, which is able to generate the A0 mode. The A0 mode goes directly through, but when it interacts with this stiffener, tends to send two more modes which along the stiffener. One is the A0 mode, which is converted into A0 mode. Another is the A0 mode that's converted into the S0 mode, the S0 being much faster. So you get three modes that seem to be receivable at the other side. And the question is, since two of these modes are traveling on the stiffener side, can we actually use it? And the answer is absolutely yes. So we see the three modes here. If you go to one of the bottom one, you see the three modes coming through. And these three modes are different for defects of different types of defect that they were actually programmed into these samples. And so not only we were able to tell the defects, we are also able to size these defects and locate these defects quite nicely. Similar applications for our light combat aircraft, where again you're seeing the flap, and the question that came up was that these are sandwich structures with ribs or stiffeners. My apologies. Previously, they should be called as stringers. These are stiffeners. So what we have done is we actually generate a wave which goes along the skin, inspects the bonding, inspects the stiffener, again inspects the other bonding, and then comes back. Again, air coupled, no water in the picture. Very nicely, we were able to see a good sample with no delamination or disbond, with a small disbond and a large disbond. So we are able to use this technology for real applications, and even more so for applications where you have to inspect the bends, and very hard to inspect the bends with the conventional technologies. So here again, a wave is generated, guided wave that goes around the bend, and it's picked up on the other side. And if there's a delamination, then the characteristics will change, and that was used for the inspection. Somewhere along the way, we happened to hit upon something that absolutely made no sense to us. And I'll just give a quick story on this. My student came back and showed me some results on a guided wave, and we were trying to inspect for corrosion in metallic structures. And when he came back and showed me the results, and I was puzzled because the results were too good to be true. Then I looked into his work and then I asked him, show me what experiment setup did he use. He showed it to me and I was a little bit unhappy because he was using the wrong transducer. So I had asked him to use a 0.25 megahertz transducer because most of the guided wave functions at lower frequencies. This guy, by mistake, or not purely by mistake, but that was because of the fact that these, when you handle the writing on these transducers, sort of fade away. So you use a 2.25 megahertz transducer, but the point in that had faded away. Because I knew the part number, I could tell what transducer he had used. And I said, so you used the wrong transducer. But then we looked at the results, it was unbelievably good. So the question that came up was, what is going on here that made these waves, when we know that the guided waves are all usually found at the lower frequencies, what is happening at these higher frequencies, about 10 times the frequencies? And that's kind of when we discovered this phenomena, which we have called it the HOMC or HOMC. And I remember when we started this, I was right. I was the one who took the photograph here illegally. And this is in Singapore. And if you look carefully, this guy is sitting on a pile of oil-filled soil. This is a big storage tank that had leaked. So we rigged up a very quick little robotic setup. And the idea here was, can I actually use it to inspect this and prevent the leakage in the future? So that is one application. Another application are the fact that pipes are supported and the support regions often are prone to corrosion. Can we do that? So as I said, in 2006-7 timeframe, we started saying, wait a minute, this may be something that we can inspect. And I'll tell you the reason in a minute or two why this is very useful. So we discovered that high frequency guided waves is possible. In fact, when I presented this in the US, several people said that I'm making a big mistake, then it is not a guided wave. Today, many of them have papers on the same phenomena. It took us about 5 years from then on to standardize it. We were very lucky that ExxonMobil, who owned this particular tank, started supporting us with a lot of samples. They didn't support it much with money, but they gave access to a lot of samples. They gave access to a lot of their facilities where we could go and examine it. We worked in Singapore, we worked in Australia, we worked in US, many other places, and in 2013, Exxon wrote a report saying that this technology actually works very well and then recommended it to all their units across the world. Since then, we have commercialized it more, and you'll see the numbers, mind-boggling numbers. In 12 countries, this is used. So here's a video of that technique being used for storage tanks. As you can see, storage tanks, if you just go north of Chennai, or near any airport, you'll see these big storage tanks. This is an example of storage tank that actually has fractured. One of the reasons why it fractures is because of corrosion that happens very close to the shell region or the wall region. So this commercial product today actually goes. This product is called TAPS, which is Tank Annular Plate Scanner. A similar, same technology also finds application, as I said, in pipe supports. Pipe supports, these are some examples of pipe support. There are different forms of pipe support that you see in the industry, but all of them are prone to corrosion, and it's very difficult to inspect that region. So here's an example of the same technology showing how we can detect these metal loss and not only detect but quantitatively map the remaining wall thickness in these materials. Here's an example that you can see where instead of a pipe, this is a boom. It's again a pipe, but not used to transport fluids. But instead, this is supported again. This is a very critical structure because this is like a crane. And hence, these are highly stressed locations. And again, we are looking at that hidden region where that boom pipe is resting on a support. And this is two engineers who are actually stationed in the high sea near Brunei doing this work. So just to let you know that HOMC was something that came out of a mistake done by one of our students. And today it's a field proven technology. Today, more than 1,000 tanks, storage tanks worldwide are inspected and monitored by this technology. More than 40,000 pipe supports are monitored by this technology today. And this has been taken forward by one of our companies that incubated IIT Madras. In 2013 or so, 12 or 13 timeframe, one of our MTech students, dual degree students, was working with a material, and we knew that this material could potentially generate sound waves. These are called as magnetostriction materials. So he he got a few of these samples made, and I told him, hey, high temperature monitoring of pipes is very important and very difficult to do today. Do you think any of these will work at higher temperatures? And lo and behold, a couple of these actually started. We showed that it works up to 350 degrees Celsius. Now, at anything about 100 degrees Celsius to 350 is a sweet spot for industries because when they operate at these temperatures, corrosion becomes a major difficulty for them and challenge for them. So, interestingly, we got a little grant from Reliance to try it out on their plant. And this was the first installation we did in 2015. And in 2016, we started a company. We call this product as GUMS. We started a company called Detect Technologies that was going to try to productize it and make it global. So the way it works is today, the way it works is that you have multiple sensors, assuming that there's a pipeline with two bends on either side. The wave can travel up to 30 to 40 meters along the length, and these are permanently installed units. And everything comes on the cloud, and then the data analysis is done on the cloud and can be done remotely. Today, this is, and I need to slightly change this. Today, we are certified up to 200 degrees Celsius, and we're trying to get it a little higher. We know that the technology can work up to 300 degrees Celsius, but getting certification, you can only go up a certain temperature every few months, and you got to wait for before you can get certified further. Today, we are able to cover 60 meters of pipeline with one sensor system. We can pick 1%, what's called cross-sectional loss today. And this technology, today we have a couple of hundred of these systems in various refineries globally. And your data keeps coming into the cloud. You can tell which month you have had a problem. and where we need to keep watching out for a problem and mitigate the eventuality by taking some corrective actions. The number of companies that are using this is quite mind-boggling, and many of the who is who in oil and gas and some other industries are using this particular technology. Again, came out of one student who actually found a material, and lo and behold, it started working at higher temperatures. Going to a similar discovery, but more methodically, we have been working on what is called waveguide sensors for a long time. This work started for me way back when I was in the US, when we were actually monitoring the viscosity of molten glass. But we were doing that with a bulk shear mode, but with a waveguide, which is much thicker and had a higher diameter. Now, when we started working later with companies like Corning Glass for characterization, there was a requirement when people started talking about, even from our nuclear industry, can we do it more remotely? Can you also measure temperature? And can we measure temperature instead of 5 or 10 thermocouples? Can we do it in one thermocouple or one sensor? So that started, and then we had 1 or 2 PhD students, 1 master's student, and finally another PhD student work on this. And over the years, we have now got to a point that we have commercialized this technology. One example of that technology is called PORTS, which stands for Portable Rheology and Temperature Sensor. And this was, 2019-20 timeframe. We have got it commercially available. So how does it work? So here's an example. I will take an ultrasonic wave and introduce the ultrasonic wave into a waveguide, which is like a rod or a wire or something. And if I put it into a fluid that is changing in rheology, or we want to measure rheology, what happens is, if you remember the 3 wave modes I showed animation about, the longitudinal, the torsional, and the flexural. And if I were to, in this case, it is a cure monitoring of a polymer. So when you start, the wave actually travels very nicely in the material, irrespective of the surrounding media. But as the resin starts to cure, it starts to bind to the surface, and that causes all these waves to attenuate because more of the wave is leaked into the surrounding. You can see that some of the modes are leaking very significantly. Some other mode, like the longitudinal mode, doesn't leak that much. Now, in addition, the time differences and any movement, if there's a temperature change, then these signals will start to shift to the right or the left because of the fact that the moduli is changing for that particular wire or waveguide that you have. So you combine this information, and then you can create a nice little sensor that can actually measure temperature and rheology, which simultaneously. Now the rheology is a function of 2 products. So one is the viscosity, and the other is the density, mass density. So you can actually measure all the 3 if you design it right. So here's an example in the bottom. What you see here is that with the same sensor, and there's a video coming up in a minute showing this, is measuring as a function of time. When we increase the temperature is measured not by a thermocouple, but by the sensor itself. And consequently, the decrease in the viscosity or the rheology is measured simultaneously. In order to do that, we had to make sure that our sensor matches with some of the calibration fluids that you see here. So these are all the calibration fluid data, or the dots, and the line is measured by our curve. So basically, there is a phenomenal matching between the standard data and what we are doing. This particular one is limiting from 25 degrees Celsius to 80 degrees Celsius. So here's an example of this in a somewhat of a live pattern. So this is a sensor's dip. We just increasing the temperature, and what you see here is, as you increase the temperature, the rheology drops down, and then we go back, and I will do a step change again in temperature. And this is live data recorded. Okay, again, you see that the sensor is providing information of both the temperature and rheology at the same location. Now, the question that comes up is, let me keep going forward, how sensitive it is. And what you see here is that this is an experiment which was done, and this was initially called a failed experiment because the student came back to me and said, hey, sir, there is a drift in the sensor. He showed me this data. And I just marked the line here and a line here and said, hey, any chance was it like 5:36 in the evening? And was this like 8 a.m. in the morning? And he checked his data and said, you are absolutely correct. This was like 9 in the morning, and the one earlier was like 6:37 in the evening. And guess what? It's very interesting. I said, why don't we look at the temperature data? And we said the temperature data is also fluctuating and kind of mirroring the same thing. And so it so happens that this is because of the fact that the air conditioner was, thermostat was turning it on and off during the daytime. At night time, there's very little movement in the room, and hence the sort of the temperature increases, and that is reflected by the rheology change in the fluid. And then come back in the next day morning, again people start coming in and out, and the thermostat is starting to react to that. We were able to see that the temperature change we are measuring is of the order of 0.2, 0.3 Celsius, and quite reliably. If you look at the signal to noise ratio, if you do a little filtering, you look even prettier. So that is the sensitivity that we could do, and we have commercialized that through a company, as I said, called Zyma Analytics in 2020, 1920 timeframe. And today they have made products. An example of product is right here, where this particular sensor is used to measure the molten properties of metals like aluminum, copper, zinc, and many others while it's being manufactured. For the first time ever, anybody has measured temperatures inside these molten materials reliably and continuously. There are no sensors that people are able to find that can do this. We are the first people in the world to be able to do this. Not only we can do this at multiple locations along the length of the thing. So we can even look at temperature profiles and molten metal, rheology profiles. So as we speak, we are trying it out on 2, 3 different industrial applications. One is aluminum manufacturing smelting companies such as Vedanta, Emirates Global Aluminum, and so forth. We're also looking at zinc and nickel manufacturers, wherein they are getting valuable information that will allow them to understand their processes better. So here are some examples of clients that we have. And what I showed you was only one application. There's a couple of other applications, but we are seeing a lot of value in polymer industry, a lot of value in metal manufacturing industries, also refineries and other process industries. So I'm getting to the conclusion of my talk to say that we're very proud, and this is a slightly old slide, actually, the numbers are wrong, but we're very proud that not only we are able to work on technologies and as well as work on science behind this technology with a lot of passion, but we've been fortunate enough to work with industries, create a value proposition in industries, find some students who are willing to risk their career and come and join a new startup and then take it forward. So this just gives you a timeline when our center was formed in 2001 to Professor Narayanan absolutely must remember that. And 2010, when IIT Madras decided to approve incubation, we started the first company and then followed up with a few more. Just to let you know, today these companies employ more than 1,100 people. The number here is a bit off. This is the probably slide was done a couple of years ago. And today there are more than about 100 intellectual property filings within these companies. And the most important thing is this 1,100 jobs are high-tech jobs created, not of which about 80% is all in Chennai, another 10% other parts of India, and another 10% globally. So they're all globally represented. So what you see here are our academic partners in big stars are our academic partners between the center and other universities and labs. The small dots are the key channel partners and key deployments of the various technologies that are there developed by the startups coming out of the center. So I just want to say that, conclude by saying that our center has an ecosystem that provides leadership technologies to not just Indian industry, but globally. And the lab to market transition is something that is amazing experience. When you see something that you thought, something that you created with no intention of this winding up where it winds up and solving a problem that it never solved, you never thought it will solve. That experience is something that's special. Even yesterday, we had a launch by Indian Oil Corporation of our new product that we have developed with them, hoping that that will also see the commercial world very soon. So thank you, INAE, thank you, Professor Narayanan, thank you, Professor Ashish Sen, and thank you all for listening to me.
Thank you, Professor Krishnan Balasubramaniam, for a wonderful journey of making products out of the research done in the lab and then incubating so many companies and with products. So I think now the Professor Ashish Kumar Sen can take over and then monitor the discussion and question answer session.
Yeah, thank you, Professor Narayanan. Hello, everyone. I'm Ashish Sen. I'll be moderating questions, your questions to Professor Krishnan. You can unmute yourself, ask question, or you can ask them in the chat box as well.
Yeah, I have one question in the sense, see, in all these developments of sort of detection, testing, and so on, the underlying philosophy or phenomenon is guided waves and their sort of transmission and the type of receiving which you are doing, and then using the change in their properties, you are able to detect the defects, failures, and so on in most of the technology which has been developed.
That's correct. Yeah, you are absolutely correct, sir. In all of them, ultrasonic guided waves is the basis, sir. Please go ahead.
Mr. A. Sanat Kumar, you have a question?
Yes. Can you hear me?
Very well, sir.
Okay. I am from the Nuclear Power Corporation. I'm a retired officer.
Wonderful.
Involved in the fueling machine of the Nuclear Power Corporation. Now, in our machine, we have a component which is a telescopic tube. Okay, the telescopic tube has at the front end, it has got a head. It keeps moving forward.
Yes, sir. You're talking about the Barsis, I suspect.
No. It's
not the Barsis. Okay.
Something similar to Barsis, maybe.
Okay.
But not quite the Barsis.
Okay.
So the telescopic tube keeps moving forward, and today, inside the tube, of course, there is water. Heavy water is there. And the back end is stationary. So the tube keeps on increasing, going forward and backward, telescopic tube. Now, we have attached a cable, stainless steel cable, to that front end of the tube. And at the back end, we have got a pulley. And as the thing moves forward, it winds a potentiometer, and we know where the thing is there. And when it comes back, that pulley is spring-loaded, and it returns back, and the potentiometer again tests. So we got a 10-turn rotary potentiometer, and we are measuring analog.
Okay.
Now, our problem is the cable that we are using tends to break, and it breaks when it is operating, and then that's a problem because the fueling machine will get stuck. So now I want to know whether you can put a transducer at the back end, ultrasonic transducer at the back end, send a wave right through the water tube, and it gets hit back and comes back. So the travel distance, you can, if you measure the time of travel, can you tell how far the front end is? Is it possible? This will work at about 100 degree Fahrenheit, you say, maximum, at least 40 degrees centigrade, 40 to 50 degrees centigrade. There is pressure in that water. It may be up to 1500 psi.
The answer is very likely it should work. There are technologies available today where people are able to even find some simple pinholes in tubes which are much longer. So what happens is that when a wave travels in a conduit like what you're talking about, every time there's a cross-sectional change, you have the physics will tell you that there should be something that's coming back, because every cross-sectional change is an impedance change. And particularly when you see the end of the tube, of the telescopic tube, I don't know how many sections you have and how long it is. I suspect
take it about 3 meters. 3 meters or
3 meters, 1 plus 1 plus 1, I suspect, right?
Oh, 1.5 plus 1.5. Take it like that.
Okay, so very likely you will get a signal from the from that 1.5. Okay, and then very likely you should get a much bigger signal from the end of the tube. For this, what you need to do is that the wave length of the wave that you're generating should have something very of the order of the diameter of the tube.
The diameter of the tube is about, I can tell you, the diameter of the tube is about 15 millimeters.
So it's about 15 millimeters.
15 millimeters to 19 millimeters, like that.
Yeah.
Yes.
So typically at 15 millimeters, given the fact that you have wavelength of say 1 megahertz is 1.5 millimeters. Okay, so 15 millimeters would be 100 kilohertz. So you probably should be somewhere between 50 kilohertz and 100 kilohertz. And if you have a transmitter and a receiver, the chances are very high that you'll pick it up. Okay. Conventional ultrasound that's used for inspection, are much higher frequencies. So you probably need in that range, maybe 50 to 150, 200 kilohertz. If you have that, then you should probably be able to pick it up.
Okay, I have not told you, I forgot to tell you a little bit of thing. The transducer, whatever you're using, should be radiation resistant. Otherwise, you should have to put a causal around it so that.
Correct. So radiation resistance is the first problem is, can you find it or not in a normal thing? Yeah. The second is, can you generate it in a way by which it's radiation resistant generation?
Yeah.
So that I think your nuclear industry knows better than me. What are the piezoelectric materials that can sustain the radiation? Okay. So you know very well that there are people have these sensors available. So I don't know if it's lithium niobate or I don't know which is this. There are many materials that are far more resistant to radiation than PZTs themselves. So you need to find that material. But I think the first question is on ultrasonically or acoustically, this is a solvable problem.
Okay. Right. So now my last question on that issue is that I am a retired fellow, but I can ask people who are working on that line to come and meet you. Will you be able to develop the system?
Yes, we do, sir. We have done a lot of work for DAE, mostly through BRNS. Yeah. But we have done some work with NPCL also in a couple of different places, because NPCL is often the end user.
Are you familiar with Mr. Baldev Raj? Dr. Baldev Raj?
Baldev Raj is my guru.
So he is
more than guru.
My friend also. Unfortunately, late.
Baldev Raj is the person who was instrumental in setting up the ND non-destructive test.
And also bringing me to India and bringing me back to India.
No, he did ultrasonic inspection of a concrete big beam, he was a reinforced concrete beam. Yeah. So anyway, I'm happy that you are friends with. I am a good friend of him. He's when he was.
Yeah, we are I lost more than a friend. I lost Guru when he passed away.
So I will try to ask these people to come and meet you.
Please, sir, with pleasure.
See the drawing. They'll come with the drawings.
Sure.
You can see, probably get a better idea than I have given you now.
Sure,
and see if it is possible to work. Because if it works, then it will save a lot of maintenance time, because the wire keeps on breaking.
So, I mean, if I can also think a little bit deeper and figure out if there are multiple approaches to the same, sir.
Yeah. Anyway, you need to know the configuration, which I have not given you very well.
No.
So with the drawings, they will come and meet you.
No, absolutely, sir. Please let them call me. You have my email ID, right? I have put it.
Yeah. Just now I have saved the print screen. Yeah.
Yes, sir. Great.
From your last slide.
So we'll be very happy to talk to them, sir. Okay. We are here to help in whatever way we can.
Thank you. Thank you very much. Thank you. Thank you.
Yeah. So, Professor Krishnan, I have a question.
Yes,
a couple of questions. One technical question and one more generic. So what is the frequency range that you normally deal with, and also the physical dimension of the defects that you were able to predict using the system?
You picked the right question to ask. As you probably guess, the frequency, or more importantly, the wavelength, defines the defect in terms of its ability to be detected. All right. Having said that, it must also be understood that the wavelength is mainly controlling the resolution of your detection and imaging, and detection is more a function of signal to noise ratio. Okay. So if I can have a very noise-free material, honestly, with much larger wavelength, I should still be able to detect the defect. Now, I may not be able to resolve the defect, or I may not be able to size the defect very well, but detection is a function of signal to noise ratio. Now, the noise, when I say noise, it should be qualified. It is noise like what you see a white noise in an instrument or anything like that. There can also be noise due to the material grain structure. The third type of noise that we get is due to the mode, multiple modes that come into your signal window.
Okay.
Because, as I said, multiple modes can exist in a structure. All right.
Yeah.
Now, the way, so if you just go and hit a structure with, and this is what we have, people are trying in the 50s and 60s. They'll just go and try to generate and try to figure out from the complicated signal where the signal of interest is. This has been changed, where now today we know how to control the wave that is generated. Even if the multi-modes that are generated, we know how to filter out the modes that we don't want. This is the mode that we want. Yeah. Having said all that, still, that's all great when you have a nice structure, all right? But a defect is something where we don't have any control over.
Yeah.
So when defect occurs, you don't have control over that. You can't, you don't know what, what modes are generated by the defect. And almost all modes, all defects will generate multiple modes. So they would be called as noise from the perspective if you are looking at trying to pick a signal that is not contaminated by these multiple modes.
Yeah.
But in some ways, it's also information. All right. To go back to the there is no clear answer to this. It is not easy problem. That is kind of where we find ourselves challenged all the time. And that's where we make our buck.
Yeah, how do you isolate, the noise from the so-called signal that you are anticipating. This
It
is
is the
not very
biggest
different
challenge.
from the noise itself.
Biggest challenge is exactly there. Now, electronic noise is much simpler to handle. Material noise is not so easy to handle.
Yeah.
And as I told you, the wave noise, as I would call it, or wave mode noise, which is the multiple modes that gets generated, is even more difficult to control. So you can't control some of them. Some of them you have to live with. And when you live with those things, what you need to do is to find methodologies to sort of reduce those effects and enhance the effect that you're looking for. All right. And that's kind of it. So which mode will not mode convert as much as other modes? Then you'll probably find that that mode doesn't travel far. Yeah. So you have to play with, and the number of modes that we can generate is unbelievable. I mean, what I showed you was a very simplified diagram. The reality is that you take, I give an example. We are working on guided waves in rails.
Right.
You know, the rails. There are about 500 modes I can generate in that rail. Okay.
Yeah.
Compared to a pipe or anything where I can generate maybe 20, 30 types of modes. And then anything about higher modes actually do not. But because the complicated shape of the rail, you have the head region, you have the web region, and you have the feet region. So basically it's a combination of three waveguides. So each one say 20 or 30, then you can generate all combinations of those. Okay, it's just not 20 plus 20 plus 20. It is every 20 can interact with the other 20. Okay, so you can generate 20 times 20 times 20. Okay, so now you're talking about I don't know, thousands of modes is possible. So again, then what do? You have to somehow figure a way to generate the mode that you want to be generated. And it is possible to actually filter the modes when they receive. So the way we do that is very simple. One easy way, there are many ways, but one easy way is if I were to use not one single receiver or one single transmitter, I use multiple receivers, multiple transmitters. Okay. So you take a very simple example. I have a simple plate. Okay. Now, if I can generate, so use multiple modes, then what I can do is if I excite them in a differential pattern, I can generate the mode I want. And how do I do that? I calculate what are the mode shape that exists in the plate, and then mimic that mode shape by say 8 transducers. So let us say the middle, I want to generate a mode that has a highest amplitude in the middle and weakest amplitude in the top. What I will do is, I will do two things. I will, of course, give the highest amplitude to the middle transducer and the weakest amplitude to the side transducer. But what I may also do is to figure a way by which I will do some phase cancellation in the top transducer. Right. Okay. So that I will almost keep it, because if you don't do that, you still get boundary conditions will keep the wave going. Right. So what I do is I will do two transducers of the boundary, and they will be phased in such a way that the wave kill each other. So the top has no displacement, the middle has maximum displacement, and I can do that. So if I want to generate the next higher mode, I may slightly change this pattern. If I have 8 or 16 of these transmitters, I can start to control them. Now, that can only say what is the wave I'm launching. The problem I also have is the wave coming back may not, I don't have control over it, because there could be mode conversions. New modes are also coming back. So where I will again use my 8 or 16 elements, and now I will back calculate and I say, wait a minute, I will only, I can, sort of use weights so that I can selectively enhance the information coming from a particular mode, which has a particular mode shape. Right. Again, going back to the same phenomena I talked about, I will probably maximize my, put a higher weight on the middle and a lower weight on the outside for a mode where the middle has the highest stress or amplitude. Right. So I can do it at, so as long as I go to this multi-element transduction, I have a lot of control over what can be done and what can be received. So this is how these are things that we learned over the last 30 years.
Right.
Okay, this didn't exist 35 years ago. So they were trying to figure out from multiple signals. Today, I can actually filter out many modes almost exclusively.
Right, right. Yeah. Thank you, Professor Krishnan. I think Farooq has a question. Farooq.
Hi, thanks, Ashish. Professor Krishnan, this is Farooq. I actually had a question on the rails, but you already said about that. So my question would be now on, have you looked or any time tested anything on building structures or maybe bridge structures where the material is more of non-homogeneous kind?
Okay, a very good question. So one of the biggest problems that if you're talking in terms of building structures, the ones that we would probably be able to address are metallic structures and not the concrete as much. Does not mean that we can't do concrete, but you can do concrete, but you get into very low frequencies to do concrete. But you can do guided wave in concrete. You can do Rayleigh wave in concrete. In fact, there are technologies available in the commercial market for generating these Rayleigh waves. And what they do is they use Rayleigh waves to measure the inhomogeneity of layered, asphalt, for instance. But we go to fairly low frequencies to do that, probably in the 10 kilohertz and lower, wherein you can penetrate reasonably deeper. So people have shown that you can generate these modes and you can tell the depth of asphalt or concrete. You can also tell that there is a delamination that is there between two concrete layers or between the asphalt and the base material and so forth. So that is done. Now, another area in civil that we see is some work going on, and in fact, Prabhu Rajagopal, my colleague, is actually had a student. Actually, he's got I think, a Kenyan student who is working on this, where we are looking at sending these guided waves in rebars that are encased in concrete. The idea here is to see if the rebar is getting corroded. So that he has got some work, and he's not the only one. There have been a couple of other reports elsewhere where sending wires through rebars has been looked at quite seriously. Another example where you might find similar for like bridges is if you have a suspension bridge, then you have these cables that are multi-strand cables that are holding it up. And again, there has been some work on guided waves being sent through these multi-strand cables. What happens is usually these cables, they fracture one at a time. And what happens is that the fracture rate increases when you start to, when one breaks, then the stresses will become higher on the others, and then so it sort of cascades itself. So that is something that people have done from two perspectives. One is to send the wave and see if there's damage. Another one also just to listen, because whenever a thing cracks, then the acoustic emission is also can be picked up. So these are what comes to mind when you talk in terms of bridge inspection.
Professor Ashish, can I have a follow-on question on this?
Yeah, sure. Please.
So the stress level in these rebars or the tension structures, do they also play a role? Because most of the current structures will be pre-tensioned, right? The bars are pre-tensioned and then kept, right? So do they change the characteristics of wave that you get or receive at the end?
The answer is yes and no. Stress does affect, so there's something called acoustoelastic constants that you can measure, wherein you can calculate the stress because the velocity of each of these modes do change. However, these acoustoelastic constants are rather small. So you have to have long, sample, or you need a very sensitive instrument to measure the change of these velocities as a function of stress. So people have developed equipment, including I have done a lot of work on this, where we have measured stress, but in a very, you need a very controlled environment in which to measure. Now, so if you're talking of rebar, maybe 5 meters, 10 meters long, the stress will affect the velocity marginally. However, if you're looking for corrosion, say, of these rebars or cracks in these rebars, the effect of stress is unlikely. In fact, the effect of temperature will be significantly more. Even 5 degrees Celsius will have a bigger change than you putting significant pre-stressing on these things. The length will change, because the length change, you may find that the time it takes for the wave to go and come back will perceptibly be measurable. But definitely you will not see the see the effect of this stress on your measuring ability to measure corrosion or cracks in these metallic structures.
So it's not that sensitive, the stress, pre-stress level.
It is extremely low now. Low. The proportionally constant or the acoustic elastic constant is rather weak. So I just give you an example. Say typically it is like 0.3, 0.4% change. Okay. So that's hard to measure. In fact, we struggle to measure. If I can measure stress well, then that is very useful to the industry. But we struggle to measure. We have not that we've not done that. We have done that. In fact, there's an ultrasonic guided wave instrument that's been available for the last 30 years. Which measures the what the quote unquote the residual stress in rail. And many of you may know that rail is has a very serious issue with buckling. Okay, and whenever a train approaches, you are putting more compressive stress onto the rail, and there are been many cases wherein the rail actually starts to behave like a snake when the train is approaching, and then that causes a lot of derailment. This is more true in the US and European countries. In India, somehow because of the temperatures or whatever be the reason, the stress related issues are not dramatically high, although there is a lot of concern here. But just to make sure, let you know that there is an instrument available where it is measures at extremely sensitive, but you can clamp this onto a rail and measure the stress of the rail. But the stress in the rail doesn't affect my ability to inspect the rail, or whether for corrosion or for cracks, because the effect is very small.
Thank you, sir. Thank you.
Yeah, Professor Krishnan, I have a generic question. I think, the talk was very inspiring, and I just wanted to get probably the audience hear from you. What are the bottlenecks that you would have faced in going from typical research lab to industry or market, rather? And because you have seen even, as a researcher and also as a dean, so if you can shed some light on that, that will be probably useful for the audience.
Okay, so let me give credit to my advisor. Okay, so he was very much in the same line of thought. So from day one, he made me work with industry. Sometimes for a reason that he loves to play golf, and every time he had a golf tee time, he would say, "Krishnan, I'm busy. Why don't you go and handle the industry yourself?" And initially, I was thinking. I did think that maybe he's taking advantage of me, but honestly, this was the best experience I could ever get. So I probably got trained very nicely by him on how to look at industry, how to look at industry problems, how to interact with industry, how to understand where is the return on investment for the industry. So, see, many of us are very passionate about science. We're also passionate about technology. At the end of the day, industry, what matters to industry is, can technology bring profit to them? Can technology solve a problem that is not solvable. They definitely, and rightfully so, do not have any interest whether your idea is novel or not, whether your idea is publishable or not. That is not something that they have any interest in. So one of the things that I have always done, and if you look at our lab performance in terms of journal papers and other things, I think we have done well. You will see that it's very comparable to most labs, internationally, and definitely within India. So the question is, how can we do that? So what I do is I partition my work in two ways. One is industry facing, the other is basic work. So we publish in some very basic journals also. So we publish in APLs and scientific reports and stuff like that on one side. So pretty much what we try to do is we look at the work and say what part is publishable, what part is can we give to the industry. And usually what we give to the industry is something that is probably not so publishable, all right? And in some way that works to our advantage, because if I were to give them and show them that I've done this basic work, then they will want IP on that. So we tend to partition our minds in two ways. One is how we can publish, how we can patent, and that should belong to IIT Madras. But then what I have patented, what I have already worked on, how can I push it to where the industry accepts it? So a lot of interactions, a lot of discussions. It's not easy to sell anything to the industry. But if you solve one of their problems, then you'll see them knocking on your door on a regular basis. And industry thinks you're a magician. You come and you can solve any problem by just clicking your thing. It's not like that. So one of the things that for me the hardest thing is to convince the industry that there needs to be patience. There's nothing I can do, and if I can do anything overnight, then somebody else can do that. So I don't want to deal with anything that others can do, then I don't want to be involved. I want to be involved where nobody else can solve this problem. Only then you come to me. So many times, whenever industry comes to me, and if I can foresee a way by which it can be solved by a company or a contractor, usually I will just tell them this is the way. I draw them and say, hey, this is how you do it. Why don't you talk to this guy? He'll solve your problem. And that way I don't get involved in many of the sort of easy problems or solutions. We try to do things that are hard to do. And we also tell them that it will take 2 years, 1 year, 2 years, maybe 3 years to get to where it is robust. So one of the key things that you realize very soon when you work with industry, and more importantly, our students find it very hard to realize, is in our lab, we can get something to work, but that is only maybe 10% of the actual job done. You have to put another 90% so that whatever that worked in the lab will work in the field. And not only it should work in the field, it should work every time the same way. And for that, the mindset is not easy, which is why the startups play a big role in the whole thing. Many of these technologies were, only to a certain point in our lab. And the same kids, they go out, then they realize, and you have to keep working, you got to keep iterating, you have to keep, and it's very boring to do that. That's why in our lab, we don't have the mindset to do that. So you need an industry mindset. So that's why the startups play a big role, because they are able to go and chug, delta X improvement every time. Every time you go try it out, something realize, oh my God, this is working okay, but something else is not working. Come back again, figure out why that didn't work, fix it, go back again, try. The number of iterations are huge. I just mentioned yesterday we launched this product for IOCL. This product is version number 22. And it is not yet in the, I have not, no startup yet. Now, a startup has to take the version number 22, and I can assure you they'll have to go another 10, 15 iterations before it really works well in the industry. So today it's working well, but it is not working to the industry standard. And then you have to get, then you have to look at certification. You have to look at standardization. That's another effort. So the journey is not an easy journey. Okay, and you have to think parallel, work in parallel, because each one takes years before it gets. Each one of the 3 examples or 4 examples I gave you has taken something close to 4 or 5 years after we thought it was industry ready. Okay, so it's taken 5, 6 years before that, maybe some longer than that. But when I felt, or when we felt it's industry ready, it is still taken 4 or 5 years after that to get to where it is accepted in the industry and you're able to provide the solution at a scale and at the level at which the industry is willing to buy it from you, because they are going to pay money, and every paisa they pay to you or to anybody has to be significantly justified. And more importantly, when a Shell or Exxon or a Boeing comes to you and say, this technology is what we would like to use, that's kind of when you really feel tickled, because, because people are willing to. That tells you that that this technology is not available elsewhere.
Yeah. Thank you. And so, Professor Narayanan, I mean, can we conclude the technical session and move on to the thank you note?
Maybe I think Farooq can give a vote of thanks. So,
okay. Thank you very much, Professor Krishnan, for making time and coming and giving us a very nice talk. It was really illuminating for me. Working as a dean and then making so many companies as a faculty along all at the same time in the institute. I joined when you were promoted the dean, and my first project was from your side in the ICSR. So I kind of remember those days when you asked questions and we answered and got funding. It was very nice. I thank all of you who have joined us, and it's like almost 1.5 hours. And stayed with us. I think that's because Professor Krishnan's talk was very much interesting, in the sense that it was not only technical, it was technical and a journey. I think it was a journey of every engineer would like to see, right? From his products to go out and making space in big companies around the world. So I would like to thank all of you to come and join. I would like Professor Krishnan as well as INAE for making this happen. Give us a platform.
No, the INAE team.
The INAE headquarters, I think we must thank for arranging this talk, and also Professor Narayanan and Professor Nandita for heading the Chennai chapter, INAE Chennai chapter, and Farooq for contributing as a member, and also the audience for listening so patiently. And of course, I mean, all of us found the talk very enlightening and, as always, very inspiring. So thank you all. Thank you very much, Professor Krishnan.
Thank you, Ashish. Thank you, Professor Narayanan. Thank you, Farooq. And thank you all for staying back. Thank you. Take care.
Bye.
Bye-bye.
Bye.